So is the microphone working all right? Sounds good. Great. So first let me thank the organizers for inviting me to speak here. I was a participant at the very first Arizona Winter School some number of years ago, which I don't care to admit. Yes, that many years ago. So it's quite gratifying to see that the event has become quite a success. So what I'm going to do today is, well, I'm going to talk about algebraic de Rham cohomology. Maybe I should start with a couple of minutes talking about the overall goal of the lecture series. The goal of the lecture series, which is entitled P-adic cohomology from theory to practice, is to, in some sense, correct a misconception about p-adic cohomology. So you may have heard of things like crystalline cohomology and so on, which sound very scary, and if you in fact try to read what the definition of crystalline cohomology, it is a little bit scary. In particular, it's not something that you could actually somehow easily write down. If I gave you some actual variety and said, here, I want to know what, I want to sort of say, compute the zeta function of this thing by looking at the action of Frobenius on crystalline cohomology, you might look at me funny. The goal of the lecture series is to convince you that actually it's quite a natural thing to do and is in fact much easier than, for instance, doing this with étale cohomology, which you might already be familiar with. I won't assume anything about étale cohomology in these lecture series, so you don't need to know what that is. But so yeah, the idea is to explain what p-adic cohomology is with an emphasis on it being explicit and computational. And to that end, I'm going to start today, in fact, the entire lecture today will be not at all p-adic. I'm going to be working exclusively with algebraic varieties over a field of characteristic 0, like so. So I'm going to be working with, I'll come back to this slide in a minute, but I'm going to be working with, for the moment, affine varieties, eventually not necessarily affine, but affine varieties over a field of characteristic 0, which doesn't have to be a p-adic field. In fact, you should imagine C is maybe K is maybe C, the complex numbers. And the reason I'm doing this, even though I'm supposed to be speaking on p-adic geometry, is that there's this common framework provided by, how legible is that? Could be better. Which comes from, this originally comes from some ideas of Grothendieck about how to express holomorphic de Rham cohomology. So in the beginning there was C infinity, smooth de Rham cohomology, which is what de Rham was thinking about. And then there was later what I guess is usually called Dolbeau cohomology. Oh, well, roughly speaking. So what I mean is holomorphic de Rham cohomology, computing de Rham cohomology using holomorphic differential forms. And then Grothendieck realized there was an algebraic framework for this, which means you can work with algebraic varieties. Let's say they're smooth, although there's also a framework for working with non-smooth varieties, but I'm not going to talk about it, over C, or more generally, any field of characteristic 0. And this framework will also be suitable for working with rigid analytic varieties. Again, mostly smooth, over a complete non-Archimedean field, which will again be of characteristic 0. So a characteristic 0 non-Archimedean field, like the p-adic numbers. Complete, of course. So the common framework is what I want to talk about, but I'm going to keep it primarily in the algebraic setting because that's somehow the most restrictive situation. If you understand the algebraic setting, you can sort of imitate the setup in the other two settings. So to begin, so I'm going to try to manage this sort of multiple technologies here. So I have slides. These slides are on the wiki under my course webpage. So I'm going to try to sort of keep definitions and formulas over here and work examples over here and sort of make other comments. We'll see how that works. So I have to start with the algebraic notion of what a differential form is, and that comes from the notion of the modulo of Kähler differentials from somewhere in chapter 2 of Hartshorne. So I have affine variety over field K of characteristic 0. So X is my variety. A will be its coordinate ring. So A is a quotient of a polynomial ring over the field K, some finite number of variables. Omega 1, or it's sometimes just called omega, is going to be the module of Kähler differentials. So omega 1 is the A module generated by symbols D of A, where A is an element of the ring. And you want relations of the form, well, you want to kill off the differential of a scalar, because you want to think of working over the base field, and so you don't want to be able to differentiate in the base field. And you want the Leibniz rule to be obeyed. So D of a product should be ADB plus BDA. And that's the module of differentials. That's always a finitely generated module over A, if A is finitely generated over K. Now, throughout these lectures, I'm going to be working exclusively with smooth objects, because I don't want to get into the details of talking about de Rham cohomology for non-smooth objects. There actually is a sensible theory, but I'm not going to address it here. So I'm going to restrict right away to the case where X is smooth. And that has the consequence, this is essentially the Jacobian criterion, that this module here is now locally free over the ring A. And now what I'm going to do is I'm going to think of elements of omega 1 as one forms, differential forms of sort of order 1. And I'm going to form higher order differential forms by taking the exterior product, the sort of the exterior power of this omega 1 some number of times over A. So elements of this thing are whether linear combinations of symbols like so, where these omegas are in capital omega 1, and you want linearity in each position, and you want the alternating property. So the wedge should be 0 whenever two factors are equal. Reminder, there are certain elements which are interesting in here because they can be written as these decomposable tensors. But if, for instance, you have, say, 4 or more variables, there are things which are not decomposable. Like this is a 2-form, which is not decomposable. This is not decomposable. Not of the form omega 1 wedge omega 2. So just keep that in mind. So now that you know what differential forms are, I can start telling you about the de Rham complex. So there's a natural map which was built into the construction of omega 1, which is the map D. It's the sort of universal exterior derivative. So essentially, you just apply D formally by sending A to the symbol dA. So I set this up so that this map is a derivation, a k-linear derivation of A. Okay? And this takes a little bit of thinking, but it's not so much trouble. This map induces maps from the omega I to omega I plus 1. And the formula is sort of as follows. If you have something like F times, say, for instance, say you have something like this, this would map to df wedge dx1 wedge wedge dxk. There's some choice of a sign depending on whether you put it on this end or this end, but I'm going to put it on the left. As long as you're consistent, this has the property that decomposed D is always 0. So you notice this thing, x1 through xk could have been any functions here. And so this term here doesn't have a coefficient in front of it. So when you hit it with D, you get 0. So you have a sequence of modules. So this is omega 0 A over K. You have a sequence of modules like so. You have a 0 on the left. And you have maps D like so, such that decomposed D equals 0. Well, we have a name for such a thing. It's called a complex. So you have a complex, which I'll write omega dot A over K. The dot means that it's a complex, and that's where the index is varying in the notation. This is called the de Rham complex of A, or X, depending on whether I want to think about the ring or the scheme. And the cohomology of this complex is algebraic de Rham cohomology. It is denoted hi de Rham of X in these talks. Yeah, I think I'll always write X instead of A, although if I put an A here, then it means the same thing. So this is the algebraic de Rham cohomology. It's just the cohomology of this naive complex of differential forms cooked out of the Kähler differentials. Notice that nothing happens above the dimension of X. This module omega 1, I should have said this before, omega 1 A over K is locally free of rank the dimension of A over K, if A is smooth. And so, for instance, if you're looking at a smooth curve, a smooth affine curve, you have something in H1, but you don't have anything in H2 because omega 2 is already 0. So there's just no complex there. This might be a little bit confusing because if you imagine topologically, well, if I take a curve, a curve over C is a Riemann surface, so it should have an H2, and in general, a variety of dimension D over the complex numbers should have cohomology up to 2D. Well, those are projective varieties. For affine varieties, that's not what happens. For affine varieties, things stop at the dimension itself. Okay. Easy example. So this is sort of a consistency check that this thing works. If A is just a polynomial ring, then the Poincaré lemma is satisfied. So H0 of X de Rham is just one-dimensional generated by the constant function because nothing else has derivative 0, and everything else vanishes. This is an amusing exercise if you've never seen this before. It's pretty clear when n equals 1 because you can just integrate everything. For higher order things, say n equals 2, you have to realize that, of course, this cohomology is closed I-forms modulo exact I-forms. So closed means the kernel of the map from omega I to omega I plus 1, and exact means something in the image of omega I minus 1 to omega I. So, of course, not every one form can be integrated, but that's because you're not using the condition that the thing is closed. Once you impose the condition that the thing is closed, then you actually can integrate everything. It's vitally important here that I'm working with characteristic 0, which will be an issue in the second lecture. But today, everything is characteristic 0. Okay. So that's basically all there is to say about affine varieties, except that you don't know anything about what the thing I just wrote down is. You don't know particularly that it's finite dimensional. I'll come back to that. But in order to say something about that, I actually have to tell you about smooth varieties which are not affine. And so to do that, I have to quickly review sheaf cohomology, which I didn't want to write down, so I put it on the slide. So let's just say I have a finite cover of X by open affines, labeled the UI. I'm sure hoping the notation is all right, but we'll see. So Ij is the collection of j plus 1 element subsets of the index set, and then for each capital J in I sub j, xj is the intersection of those guys. Remember, my X is smooth, so it's certainly separated, so intersections of open affines are still affine. So if I have some sheaf, which only needs to be quasi-coherent here, but in these lectures it's always coherent, there's a check complex. Basically what you do is you take the cohomology, you're trying to take the cohomology on the whole thing, and so what you do is you take global sections on every intersection of, every possible intersection of terms in this cover. This is more easily said than read, so I won't try to read it. Right, in dimension 0, in step 0 of the check complex, you just have the sections over the individual open affines, and then at step 1, you have the twofold intersections. At step 3, you have step 2, you have the threefold intersections, so on and so on and so on. There's a differential which amounts to, if you have, actually, let me go back to my original plan. It's to just do this in an example. So that's what's going on in general. Well, let me just look at a particular example. So say you have, say X is the union of two opens U1 and U2. Those are U's, and that's a union. Then what do you have? You have 0 goes to the sections on U1 plus the sections on U2. This is step 0 of the check complex. And then you go to the intersection. And the map here is if you have section S1 and S2, it just maps to its difference up to some sign. I think it's S2 minus S1 in the sign convention I gave, but there's somebody in the room who's much better at minding sign conventions than me, so I'll let him tell me if I'm right. Anyway, so the point is, in general, if you have more opens, there's more complicated combinatorics. You have, say, if you have 3 opens, you'd have 3 terms here, you'd have 3 terms here, and then 1 term at the end. And so the cohomology of this complex computes the sheaf cohomology, essentially because sheaf cohomology, I mean, things are acyclic on affines. Okay, so that's how you compute sheaf cohomology for a single sheaf. But what we want to do is take the de Rham complex on X. So if you have X, so say X is smooth but not necessarily affine, then omega 1 still makes sense, but now it's a sheaf. It's a coherent, locally free sheaf of OX modules. And of rank, the dimension of X over K, assuming this is constant, which it always will be in my talks. So this is not a module over a ring anymore. It's a sheaf of finite locally free modules over a sheaf of rings. And now, if you want to write down the complex, you can't just look at the individual terms of the complex anymore. You have to sort of watch both the individual terms of the complex, and so you will have to watch the cohomology of the individual terms of the complex and the cohomology of the complex itself. So what you do is you put together a double complex by taking check resolutions everywhere. So you get this thing, and so this is not going to actually stay up, and what you do is you flatten it into a total complex. So you make a complex where, here's a trick I'm going to use. I'm going to use the copy of that diagram in my notes. Is there a zoom on this thing? There is. Excellent. So this cohomology is taken of this total complex. This total complex consists of, so C0 of the total is this term, and then C1 of the total is these two terms. So this is C0 of the total, C1 of the total, C2, and so on. So you take a diagonal thing, and you have to put the differentials together in such a way that you actually have d composed d equals 0, and this requires fudging the sign in one direction. Again, one could spend a long time worrying about how to properly put these signs in, but as long as what I'm saying is internally consistent, I won't sweat it too much. Even if it isn't, well, such is life. So that's what happens when you take the cohomology of something which is not affine. So the de Rham cohomology of a non-affine is the total cohomology of this complex coming from the Ram complex. This process of taking this total cohomology is generally known as taking hypercohomology. Hypercohomology of a complex of sheaves. Yes? Exactly, yeah. Yeah, they are in general not acyclic. Yeah, maybe I'll mention, I have an example coming up, so maybe I'll say some of these things in the example. Yeah, so you have cohomology both coming from the individual terms of the complex and from kernel mod image in the whole complex. And so you have to somehow integrate these two contributions. Notice this has the funny effect that you can now get cohomology higher than the dimension. For instance, in my example where I had two opens, you can have terms here, 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 and here. So if you have a curve, you have a curve covered by two affines. In general, any curve can be covered by two affines. Then you get this part of the picture. You get a C0, a C check 0, and a C check 1 because you have single intersections and double intersections. But you also have two rows because you have two terms in the complex, the original complex. And so you can actually get an H2, and it will sit here, even though each term only contributed up to H1. So there's sort of a shifting around that happens. OK, I owe you an example, so let me do an example. So let's go back to an affine example for a minute. Example too high. Oh, I need to zoom out. That's the problem. Let me zoom out a little bit further. Great. So the example is going to be an affine part of an elliptic curve. So x is going to be spec a, where a is y squared minus p of x. P of x is x cubed plus little ax plus b. So, and you want p and p prime have no common roots, i.e. p has no repeated roots, so that you actually get an elliptic curve when you put in the point at infinity. So this is an elliptic curve minus 1 point. And since my characteristic is 0, I don't have to worry about whether Weierstrass equations are OK, because they are. OK, so how would I actually try to write down the Drum cohomology of this thing? So first of all, I'm going to tell you the easy stuff. H0, it's easy to check, is still one-dimensional, generated by constant functions. Hi vanishes for I bigger than 1. And the interesting question is, what is H1? So what is H1? So we only have to figure out what one forms are exact, because every one form is closed. There is no omega 2, because we're on a one-dimensional smooth thing. So what is omega? Omega 1 is generated by dx and dy modulo of the relation 2y dy minus p prime of x dx. You just differentiate the relation that defines, a is k of x, y modulo this, modulo that. So you have to mod out by the differential of a relation, and so there's two generators and one relation, and you might think, well, so I know this is locally free on one generator because A is smooth. Is there an actual free generator of this thing? In fact, there is. So here's how to make it. Now, I have two different capital A's in my notes. And I think to avoid getting myself confused, I'm going to be consistent with that. So this capital A is maybe I'll write A of x to clarify. So choose polynomials A and B such that A times P plus B times P prime equals 1, right? Because P and P prime have no common roots, I can do this. And now I'm going to define the the form omega to be this clever guy, and you'll see why it's chosen this way in a moment, except I've run out of room, so I have to scroll. Now, the reason I did this is because I can rewrite everything in terms of omega. So dx is just y times omega, because I get to mod out by p, and dy is p prime over 2 times omega, if I did this right. And so the point is that everybody, so omega, capital omega 1 is just a times little omega. So in other words, you can rewrite everything in A can be written as polynomials in x plus polynomials in x times 1 power of y. So if you want to do this calculation and figure out what the de Rham cohomology is, all you have to worry about are forms that look like this, because this is everything. Okay, now how would you actually check whether something like this is exact? Well, the way you check whether something is exact is you just write down a generic 0 form, which is to say a function, and differentiate it and see what it looks like. So if you differentiate something like what I have e plus fy, because I was calling my coefficients c and d. So if I have a generic, so I'm asking about, so I have c plus dy times omega, and I want to know, is this exact? Well, what I do is I take, let's scroll some more. At this point, you don't need to know so much about what omega is. So just little omega, so you just need that. So you just differentiate this thing, and again, if I did all my algebra correct, but this has been checked once before, so hopefully it's right. So you differentiate, and so prime is always going to mean derivative with respect to x, just because I don't want to write d dx a lot. That's dx. Good thing I can change y's to x's. And using the relations, I should get something like this. So, of course, I can write it as some multiple of omega. I don't want you to worry too much about the details here, but the point is that I'm not doing anything complicated. This is not rocket science. So in particular, what does this tell me? Well, if I just take f equals 0, then I can isolate e prime times y times omega. So that means that d times y times omega is always exact, because I can just integrate d to get e. And what's left, and if you just stare at what's going on here, you could see that you could clear terms of e except in degree less than or equal to 1. Basically, if you look at what you're trying to clear out of this, if you look at what you're trying to do with this term, you can arrange this thing to kill off any quadratic. If you take f to be a constant, then you get a quadratic thing here. If you take f to be linear, you get a cubic thing here, and so on. And the leading coefficient here you could check is, so if f is c times x to the e plus all order terms, then the leading term of this x contribution is something like 3/2 plus d times cx to the d plus 2. This is never 0. So you could clear anything in degree 2 or higher, but you can't get rid of the constant in the linear term. So lo and behold, the conclusion is H1 de Rham is generated by omega and x times omega. That's the span of k span of omega and x times omega. So it's two-dimensional, which kind of makes sense because, well, you know the complete elliptic curve topologically has its middle Betti number is 2, because it's twice the genus. And this is saying if you take out one point, then you haven't changed the genus, or you haven't changed the Betti number. And let's see, is that going to be on this next slide? I don't think it is. I'm not there yet. So I'm going to mention one more thing about this situation. So remember, x was a projective curve of genus G, G equals 1 in this case, minus n points where n is 1. It's not grammatical, but you know what I mean. Because I want G and n to be general. And so, as it turns out, the dimension of the de Rham cohomology of X, in general, if you take a projective curve of genus G and take out n points, then one can calculate what this dimension is. Well, it's of course 2G if n equals 0. This is what you expect. And then the first point doesn't cost you anything. But after that, it's, plus n minus 1. You add dimension every time you take out a point. Except the first point, you don't take anything out. Or you don't add anything. This is an exercise in the notes, I believe. This is H1, I'm sorry, because, yeah, the other dimensions are easy to check. H0 is always one-dimensional. And dimension of H2 is 1 if there are no points taken out, and 0 if there are points taken out. N is at least 1. Let me scroll. Am I visible? Yeah, I'm working two different technologies here, so my brain is a little bit full. Okay. Right, and remember the comment I made is that you can get H2 when you have a non-affine curve. A curve of genus, whatever genus, if you take out no points, it's not affine. But if you take out even 1 point, it's already affine. So you lose everything as soon as you take out 1 point. But when you have no points, you can actually get some H2. And the other thing to notice maybe is that H1 of the complete curve is two-dimensional, even though there's only one holomorphic differential on the entire curve. Because the omega I had before, omega was holomorphic everywhere because omega was dx over y, but x times omega was not. So somehow x times omega is coming from a class on H2 which is not represented by a single holomorphic form. That's the checky part of the cohomology. If I was going to say that more precisely, I would say it in terms of the Hodge filtration, but let me not do that right now. Okay. Going quite quickly. So part of why Grothendieck did this, most of why Grothendieck did this originally, is that he was thinking about the cohomology of algebraic varieties over C and their de Rham cohomology, which had originally been understood in analytic terms. The holomorphic de Rham cohomology that I referred to earlier, you could think of it nowadays as exactly the same construction as I gave, but using analytic sheaves rather than algebraic sheaves. Of course, when you work with an analytic space, you don't have to work with these silly covers by open affines. You can work with much more sensible covers consisting of contractible opens on which everything is acyclic. So you don't have to deal with this check stuff, but you could if you wanted to. Now for rigid spaces, of course, it's much harder to talk about little contractible pieces that cover the thing well. So it's much better to think in terms of the algebraic picture. So part of this is propagated that maybe the complex analytic picture should also be thought of this way, so that you have a uniform framework. In any case, if you look at what goes on for k equals c, k is the complex numbers, there is a natural map from the algebraic de Rham cohomology to the analytic de Rham cohomology. And this is what is called analytification. This came up briefly at the end of Brian's first talk. First talk? Or was it the second talk? It came up briefly this morning that you can take a scheme of, say, locally of finite type over C and turn it into an analytic space. And if you start with a smooth variety, you get a smooth complex variety, so you can think of it as a complex analytic manifold. And every algebraic form gives you an analytic form. So you naturally have a map from algebraic cohomology to analytic cohomology. A priori, you don't know whether it's injective or surjective, but it's something. It's a map. And then the thing that you notice is that if X is, say, projective, or even proper, if you read the back of SGA1, you can apply Serre's Gaga principle, which says that computing, well, among other things, it says that computing the cohomology of a coherent sheaf, or actually a whole complex of coherent sheaves, if you start out with a bunch of algebraic coherent sheaves, and you compute cohomology in the algebraic category, and then in the analytic category, you get exactly the same thing. Gaga also says that even if you had a coherent sheaf in the analytic category, it actually came from the algebraic category. But here, the de Rham complex already starts out being something nice and algebraic if X is algebraic, so I don't have to worry about that. So Gaga tells me that this map is an isomorphism. That's not the pointer. This is the pointer. This map is an isomorphism whenever X is proper. And using that, Grossi-Dieck showed that this de Rham cohomology is actually finite dimensional even if X is not proper. I mean, that follows from having this arrow because analytic de Rham cohomology is finite dimensional by, say, Cartan's theorem. But you get it also in the algebraic situation, and not just for projective things. You also get it, say, for affine things. Now this, yeah, this wouldn't work so well on the analytic side, but it works great on the algebraic side. So this de Rham cohomology is actually always finite dimensional, even when X is not proper, and so you have no right to assume that the de Rham cohomology would be finite for, say, an affine thing, but it is. Now, here's somehow the point, from the point of view of this Arizona Winter School, if K is a complete non-Archimedean field, you can run exactly the same discussion using rigid analytic de Rham cohomology. So use the same setup as for algebraic cohomology to talk about analytic de Rham cohomology, and you get a comparison map, and for smooth proper varieties, you get an isomorphism, like so. And that's going to be extremely important in the next lecture, because that's going to give me a way to write down something algebraic, de Rham cohomology of a variety over, say, the rational numbers, and have it inherit a Frobenius action from the situation and geometry and characteristic P. I should be stopping periodically to ask for questions, I suppose. Or maybe I just wait till the end. See if there are questions. Or just interrupt me. Let's move on. OK, so actually, before I explain what's going on here, I should point out why the next slide exists. The next slide exists precisely because this isomorphism only happens when X is proper. If X is an affine, you would still like to be able to say something about how algebraic cohomology relates to analytic cohomology, again, because I want to do this in the rigid analytic situation tomorrow. But in today's lecture, I can talk about it in the complex analytic setting. And the way you deal with this is by introducing what are called logarithmic differentials. So let me give myself some paper here. So I'm going to be talking about a smooth pair, and right now I'm going to do this over a field, but in later lectures I'm going to need this over a base. So in general, X is going to be something smooth, and if I want it to be proper, I'll say proper. And Z is going to be a relative strict normal crossings divisor. What does that mean? Over a field, that means that the components of Z are smooth, and they meet transversely. So you have individual components meeting smoothly, sort of smooth things, and they're being transverse. I'm a bit uptight about these things, and so I'm not going to allow my divisors to have self-intersections. So I'm not going to allow something like this, but in fact it would be completely harmless to do so, because that's étal locally the same as this, right? Étal locally, what's going on is x basically looks like some piece of an affine space, and z looks like intersection of hyperplanes, coordinate hyperplanes. So we only need this for a field right now, but tomorrow I'm going to have this happening over something like ZP. So I need the general definition. So this is the situation in which I'm going to talk about logarithmic differentials. There's actually a much richer theory of logarithmic stuff, where stuff is pretty much any geometric thing you want, logarithmic schemes, differentials on logarithmic schemes, smooth morphisms between logarithmic schemes. This goes back, well, the key reference is a paper of Kato called Log Structures of Fontaine-Éleusis, which defines what a logarithmic scheme is and basically generalizes what I'm about to say here to an extremely more flexible setting. But let me just stick to this picture for the moment because it's pretty geometric. Okay, what are log differentials? Logarithmic differentials are essentially differentials where you throw in things that look like d log. So d log of a thing is, of course, the logarithm might not make sense, but the derivative of the logarithm makes sense even if the logarithm doesn't. It's just f prime over f, right? Or maybe I should write this as df over f, because I want to think of this as an exterior differential. So when I write d log of something, I mean df over f. And so what the sheaf of logarithmic differentials on x, well, you should think of it in terms of an affine. So think about x being affine. So u is the complement of my divisor. So logarithmic differentials on x can be generated in one of two ways. You can take actual differentials on x, regular differentials without poles, or you can take things that look like df over f, where f vanishes only along your divisor. So for instance, if I have x is spec kxy, and z is the vanishing locus of x times y, so I have the plane and two coordinate axes, then the log differentials, how am I notating this? Omega 1 xz over k is generated by dx over x and by dy over y. But you can't have something like dx plus dy over x plus y, because x plus y does not vanish in the right places. But x and y vanish on my complementary divisor, so you're allowed to take d logs of those. And you also can't have 1 over x by itself. You also cannot have dy over x is no good, because that's not a log differential. It's not d something over something times other stuff. So these logarithmic differentials were known to be important in analysis for a long time. I'm not sure who really originated the thinking that these were important in algebraic geometry. I want to say Deligne, but I'm not 100% sure he was the first. But the following statement, I'm pretty sure, is due to Deligne. One on the next slide. So I'm going to take exterior powers of these log differentials, and I get logarithmic I forms. So here, for instance, dx over x wedge dy over y is a logarithmic 2 form. And what happens now is that if you take log differentials on x, you can just forget about the fact that z is there at all. You can just throw away z and you get actual differentials, right? Because the only bad stuff happens at the divisors in z. You're not allowed to divide by anything which vanished somewhere outside z. So on u, the complement of z and x, you have honest differentials. And so you get some map. And it turns out this is actually an isomorphism at the level of cohomology, of hypercohomology. So I think I implicitly assumed u is affine in this, because this is a straight, well, that's fine. It's hypercohomology of the de Rham complex on u. So what I'm saying is the hypercohomology of the de Rham complex on u is the same as the hypercohomology of this log de Rham complex. And you have to put, I mean, you should think of them as both being on x. But of course, you can calculate the one on the right, you can calculate it on u. So what's the point? The point is that this sort of thing is defined on x, so it's susceptible to gaga. You can pass from algebraic to analytic with this thing. And therefore, this thing, which is the algebraic hypercohomology, is the same as the analytic hypercohomology, which is finite by Cartan's theorem. So that tells you that this thing, this HI de Rham of U, can be interpreted analytically, and it's finite dimensional. So using Hironaka's theorem, you could then think of this as another way to get Grothendieck's theorem. I mean, Grothendieck used Hironaka also, but he didn't say explicitly things in terms of log differentials. Okay. Yeah, I have in my notes something about why gaga is true in rigid analysis, but I'm not going to say anything about that. Yeah, the best way to understand why gaga is true in rigid analysis is to read Serre's paper in complex analysis, because there's no better reference. I mean, if you need the proper case, then you have to go to SGA1. But okay, so what am I doing for time? Oh, I have about 5 minutes. I don't have too much more to say right now, actually. I'll maybe mention one other example, because I have time for it. I actually wasn't planning to mention this, but yeah, I'm on my last slide over here. So I'll mention one other example that I won't talk about in detail, but is a really nice example. Another example, if you take a smooth hypersurface in projective space over your field K, then you can compute the cohomology. Sort of the interesting cohomology in this situation is the middle cohomology. So this thing has dimension n minus 1. So hn minus 1, let's say this is x. This is the only, so to speak, interesting space, because the other ones are all determined by the Lefschetz hyperplane theorem. Essentially, the cohomology of, maybe I'll mention this, this is also an exercise. The cohomology of projective space the dimension of this, is that visible? Is 1 if I is 0 to up to 2n, and it's 0 otherwise. This is actually a really nice exercise if you've never done this before. You have to use the cohomology of certain coherent sheaves on projective space. So it's a good review of chapter 3, section something of Hartshorne. But anyway, so this cohomology is quite simple, and so you can determine all of the cohomology of x from projective space except this one. This is somehow the interesting one. And the way you determine this one is you get sort of an isomorphism. I'll say what sort of means to the cohomology in dimension n of this thing, Pn minus x, which I'll call u if I need a name for it. The diddly part means there's an ambiguity of a one-dimensional space, because if n is even, then there's actually a one-dimensional piece of this which comes from here, and you're supposed to throw that out when you go to here. So this actually is the so-called primitive middle cohomology of x. And here's the beautiful thing. This u, the complement of this smooth hypersurface in projective space, is affine. So you don't have to do any hyper nonsense. On u, you actually can just directly compute the cohomology using differential forms. This thing is n-dimensional, so every n form is closed, so you only have to figure out which are the exact n forms. So this is very much in the spirit of what I did earlier with the elliptic curve. This was worked out in a beautiful pair of papers by Griffiths called On the Differential Equations Satisfied by Period Integrals, volumes, parts 1 and 2. And yeah, this is quite effective if you actually want to compute something to relate it to the de Rham cohomology. So for instance, in the next lecture, I'm going to tell you how to compute, for instance, how to compute zeta functions of some varieties in characteristic P. So I'll focus on the example of the elliptic curve, how to compute, say, the zeta function of an elliptic curve in characteristic P using algebraic de Rham cohomology. But you can also do something like this for these smooth hypersurfaces. This is sufficiently simple to do that you could give it to an undergraduate. And so, in fact, I tried this. I gave it to 2 undergrads, one of whom is in the room, David Rowe sitting in the back, and Tim Abbott. And they, in fact, were able to do this calculation and actually compute some zeta functions. So that's sort of a criterion by which this sort of thinking gives you computable results, which is that you can set an undergraduate project. I mean, of course, Tim and David are not ordinary undergraduates, so it's sort of an unfair comparison. But well, at the time, they were not ordinary undergraduates. Right. Tim is a senior, and David is now a grad student at Harvard. But at the time, they were no ordinary undergraduates. But even so, it's hard to imagine, a project involving, say, a tall cohomology that you could give to any undergraduate. Okay, except maybe some even more exceptional undergrads. No offense. But it's not, that wouldn't be really a fair thing to do. Whereas these kind of cohomology calculations that are related to de Rham cohomology are explicit enough that they're actually things you can sort of do in practice. Maybe a better test than using undergraduates is when I said theory to practice, the practice, one of the examples of the practice of this stuff is cryptography. So I might have a word or two to say about this tomorrow, maybe not, but just to conclude for now, I'll mention that when people, such as me, but also some other people, started thinking about p-adic methods for computing zeta functions and computing with p-adic cohomology and so on, this seemed like an abstract enterprise until we were able to start computing zeta functions of things like hyperelliptic curves. And then suddenly all these cryptographers were interested. So, whether they really should be interested is debatable, but it's certainly a good application for me in terms of applying for research funding. And more broadly, to make what I'm doing accessible to a broader audience. That this p-adic cohomology stuff is sort of crazy, but actually it tells you quite concrete things. Maybe I'll leave it at that for now, and we'll pick it up tomorrow, where I'll actually talk about something p-adic. I'll show you how to use this setup to actually construct a cohomology theory for varieties in characteristic P, where de Rham cohomology is not such a good idea. So, thank you. So the question is, why does it matter what the interaction is between the sheaf cohomology and the cohomology of the complex? That's most easily said in terms of spectral sequences, which I didn't mention, but I drew lots of pictures of spectral sequences in the notes. So if you take this, I can use the document cam to show you my pretty pictures of spectral sequences. Except I don't know which one of these is right. Well, maybe I'll just show you the Hodge de Rham spectral sequence. So the general thing that happens is if you have a double complex, you can turn it into a spectral sequence. In fact, this is a property of filtered complexes. You can turn a double complex into a filtered complex, actually 2 different ways. If you do that here, one of the things you get is a so-called Hodge de Rham spectral sequence, where you first, essentially what a spectral sequence for a double complex does is it tells you, okay, go ahead and first compute the cohomology in one direction. So in this case, we're just going to compute the cohomology on the individual sheaves. So that's in the horizontal direction. So just compute the sheaf cohomology of each term, and then try to put that together to make the cohomology of the whole space. Well, of course, in general, when you have a spectral sequence, there are going to be higher differentials, which correspond to the fact that you really can't separate these computations. Sometimes you get lucky, though, and the spectral sequence degenerates. And that's what happens with the Hodge-de Rham spectral sequence. It's already degenerate at this term, which basically means that you have a filtration on each de Rham cohomology consisting of pieces like this. So for instance, if you have H1 of x, sorry, let me do it this way. H1 de Rham of x, inside it, there is the cohomology of the sheaf of differentials, but there's this other piece which is the H1 of the structure sheaf, which is omega 0. So you have H0 of omega 1 and H1 of omega 0. Oh, I'm sorry. I'm going to have to zoom back out. There we go. So yeah, you have this thing trapped between H0 of omega 1 and H1 of omega 0. In general, if you had H2, there'd be a filtration where the steps are H0 omega 2, H1 omega 1, and H1 omega 2. This is the so-called, this is the Hodge filtration that I didn't talk about earlier. And this is the sense in which there's an interaction between the two. And you can see why H2 is going to have something in it, because H2 is going to have H1 of omega 1. So that's how you can get something in H2, even when the pieces only give you things in H1. If that's not a fair answer to the question, you should feel free to follow up.